All right, welcome to the Explainer. We are diving straight in today because we're looking at, honestly, a massive paradigm shift in the very foundation of computational theory. We're talking about challenging a rule that's literally governed computing for almost a century. We're moving way beyond the idea that a program fundamentally has to finish. Instead, we're going to explore what happens when you just unleash a continuous, self-reproducing automaton. But to really understand where we're going, we've got to look at where we started. There's this classic 1966 BBC archive feature that looks back at a surprisingly simple question posed by English mathematician Alan Turing back in 1936. He asked, are there any limits to the kinds of problems that can be solved by computation? And man, that single question basically birthed the boundaries of how machines think. Turing wasn't just, building a neat gadget, he was stripping computation down to its absolute bare essentials.
So here's our roadmap for today. We're going to cover the foundation of computation, the required stop state, a non-halting alternative, Pythagorean metal architecture, the scale symmetry base exponent, and finally, reimagining digital execution. Let's get right into it.
Section 1. The foundation of computation, where it all began.
Right, so think about the classic Turing machine. It's this brilliant theoretical device that moves along a tape divided into squares just reading symbols. And it operates in 3 supermechanical steps. First, it reads a scan symbol. Second, it replaces its current state based on a function table. And third, it moves left to right. That's it. It translates pure math into these step-by-step physical movements, basically chugging up and down a tape to transform symbols. But here's the catch. To actually give you a usable answer, it completely relies on one very specific rule.
Which brings us to Section 2, the required stop state, finite executions.
See, for a finite machine to actually spit out a result, there's one absolute non-negotiable requirement. It eventually has to terminate. Take a look at the legacy 1966 MUMPS programming language documentation. The halt command literally tells the program, hey, shut it down, terminate. In a Turing machine, this happens when the function table tells the machine to basically read a blank, write a blank, change absolutely nothing, and just stay put. The machine stops. It halts. And honestly, this is the bedrock of all classical computing.
But what if the machine just never stops? And I'm not talking about, your laptop completely freezing on an endless loading screen. I mean a system intentionally designed to abandon this foundational rule entirely. What if a database and the code running it weren't built to hit a dead end, but to continuously evolve?
Let's look at Section 3, a non-halting alternative, continuous evolution.
So take a look at the Hierarchical Script-Database, or HSDB, which was conceived by researcher Kyle McLean-Smith. The contrast here is pretty mind-blowing. Over on the left, we've got the standard Turing machine. It halts, it uses finite states on a linear tape, and it treats data and instructions, the nouns and the verbs, as totally separate things. But then on the right, we have the HSDB architecture. This thing is non-halting, it's self-reproducing, it actually uses fractal coordinates instead of a linear tape, and it treats code and data as isomorphic, meaning they are structurally the exact same thing. It completely merges the application and database layers into one single self-evolving runtime kernel.
Moving on to Section 4, Pythagorean metal architecture, math of the infinite.
Okay, so what makes that possible? It's a mathematical framework called Pythagorean metal. It models both data and execution as a non-halting, self-reproducing automaton, rather than your standard static state machine. The real magic here is that it totally leaves behind the standard loop around we see in classical coding. Instead of a loop that eventually hits a stop state, it uses a pointed infinity loop around. It pairs a finite sequence with an infinite number line sequence to build these incredibly complex, fractal, and recursive structures.
And it all traces back to classical Euclidean geometry. Think about the classic formula for the diagonal of a right triangle. In this specific architecture, if you algebraically remove the orthogonal measures, so sides A and B, from that diagonal C, you are left with an irrational, non-halting value. It represents this physical ideal problem. It maps out a scale-symmetric geometric pattern rather than just pointing to some static block of computer memory.
Which naturally leads us to Section 5, the scale symmetry base exponent, fractal coordinates.
All right, let's dive straight into the engine of this whole thing, the formula, C minus B over A to the n. This is the scale symmetry base exponent, and it drives the entire self-reproducing database. Think about it. Instead of storing your data at some boring linear memory address like, I don't know, sector 4, block 2, this exponent generates an infinite stack index. It creates highly unique fractal coordinates for your data structures. And because the execution path of the code and the retrieval path of the database are governed by this exact same mathematical coordinate system, that annoying object relational impedance mismatch we always deal with in traditional databases, it just completely vanishes, literally gone.
So when you actually run this in practice, say inside an SVG rendering engine, the flow is just incredibly seamless. The main process triggers the Pythagometal math, which then dynamically manages everything. We're talking size animations, coordinate recording, structural modifications on the fly, all through these dynamic nested loops. The math acts as the scaffolding kernel that manages state continuously. No stop state required. Honestly, when you really wrap your head around that, it is absolutely mind-blowing.
All right, final section. Section 6, Reimagining Digital Execution, Physical Payoffs.
So, we've talked a lot about abstract math, right? But what actually happens when we unleash a non-halting loop into the physical, real world? The architecture documentation puts this perfectly, and I love this quote. The human pilot applies the intent, but the agent cell executes the sweat bridging, that massive gap between messy human desire and strict deterministic machine execution. They call this the semiotic bridge. It's literally the translation of pure, mathematically verified digital truth straight into physical reality. And that brings us to the Flow X42 cheerbot, proving that yes, infinite math can actually be surprisingly adorable. Tucked inside this little shell is a localized Raspberry Pi Micro host. It just sits right there on your desk, calmly reading the bit-perfect on-chain state we were just talking about. It acts as an edge execution node, and what it proves is that a non-halting digital protocol can safely bypass centralized middlemen entirely and trigger actual real-world action. Here's how that final, rapid sequence plays out. First, the bot synchronizes its state on the Flow or Polygon network. Next, the local node parses the commands using that nested seed tree DB architecture. Then it quickly handles any UI rendering if it needs to. And finally, the physical actuation. That verified digital tip literally fires raw electrical signals right into the tiny GPIO hardware pins on the Raspberry Pi. Pure math spins a motor or, flashes a light. It's incredible.
We've traced a pretty wild journey today, you guys. From Alan Turing's halting tape, to a mathematically continuous database, all the way to a physical robot waking up on a desk. The technology is already here. That semiotic bridge, it's completely built. So, I want to leave you with this final question. When these bit-perfect promises start orchestrating reality right in your own living room, what are you going to program them to do? Thanks so much for joining me on this explainer. See you next time.